Hello, my name is Jonathan Apostle, and this is my fourth lab report for Physics 2211. The purpose of this lab was to predict the motion of the mass at the end of a spring, given the spring constant. We could compare this to the motion of a computational model which had the same parameters. This is option 1. The fundamental principles and models used were first Newton's second law, which shows the law of conservation of energy. Also, the energy principle, which utilizes the potential energy of the spring, the potential energy of gravity, and the kinetic energy of the system are also important. The main result was that we determined how similar the observed position in the x and y direction correlates with the computational model, and we determined that these were relatively similar, but there was slight variation. Here are the equations and why they are relevant. First, kinetic energy is proportional to velocity. Also, the gravitational potential energy is proportional to the displacement of the object. Also, the spring potential energy would be proportional to the length of it, how much the spring is stretched or how much it is compressed. Also, it's important to know that the total energy is conserved throughout the entire system, therefore the system is closed. The force of gravity is constant. The spring constant we can calculate, but we are also given it. And then the length of the spring is proportional to gravity. So as you can see in this rough figure that I drew, the mass of the system can oscillate up and down, or it can oscillate left and right. Here's the system and surroundings for the experiment. The system is going to be the spring, the mass, and the earth, and the surroundings are going to be nothing. This is important because the system is closed and there will be no loss or gain of energy in the system. Here are the initial conditions for the experiment. First, the time and velocity will be 0 meters per second, and then the initial position would be this. I got this from Tracker, and these were all given to me, the mass, the spring constant, and the initial length of the spring. So for the experimental section, I just placed the point on the center of mass after the spring had been released for the whole duration of the video, therefore I could completely observe the oscillation. Now, looking at my coding, first, after incorporating my initial conditions as previously stated, I specified my L vector, ensuring that I matched both the L and L hat. I also included S, which is the length of the spring. Next, I then identified each element of the energy within the system. After this, I identified each element of force in my system, which included the gravitational force, the spring force, and the net force. And again, this was previously stated in the main physics ideas and the key questions earlier. With this, I could then update the velocity and position. Finally, with all this information, I then needed to update all of the energies in the system. As seen in the figure, my computational results closely mirrored my observed results from Tracker. However, while they are very similar, they are not identical. Most likely, the biggest source of error comes from the physical aspect of the experiment, where I couldn't really find the center of mass very easily with Tracker. In other words, I might have had difficulty tracking the center of mass. For what if part number 1, in this example, the energy principle is satisfied, as seen by the net change in energy. While potential gravitational, potential spring, and kinetic energy do fluctuate in the system, the total number of energy does not. This is indicative of a closed system. Alright, now for part number 2, I estimated my oscillation periods by taking the average distance between oscillations in both the x and y direction. These estimations closely mirror my actual result, yet they are not identical. This is important because these would affect a number of aspects of my model, such as the spring force, the spring constant, and the spring potential energy.